So today, as we promised, as we discussed last time, we will finish at 1:45 p.m. And we finished it last time. We finished it the chapter 1. About the general, really general stuff about the statistics and this time we will go, we will enter the world of probability. But still, it will be quite easy, and most of them are what we already learned from our high school. So hopefully I'll move very quickly in this chapter. So okay, so the first thing that we learn is this sample space. Okay, so sample space is basically the set. Okay, what is the set in Korean? 네, 집합이죠? Okay, so this is not clearly a set because it involves these redundant entry. So when talking about the set, we only talk about these the set of basically the set of unique items, right? So we don't allow the redundancies. Okay, so let's keep that in mind. And so the sample space, back to this definition, the sample space is all the possible outcomes after you kind of obtain the sample from a particular probability distribution. So for example, if you roll a dice, and then all the possible scenarios or outcome or result will be 1, 2, 3, 4, 5, 6, right? So all the 6 different results, the set of all these entries are called our sample space. And so here is one example of the sample space. So here we made the situation a little bit interesting. So at first, we flip a coin. And then this is a head and this is a tail. Okay, so this is... Okay, but if we see head on our coin and then we flip another coin once again, but if we see the tail and then we now turn to the dice and then roll the dice, and then after these 2 steps, as a result, we will have all the possible different result will be composed of these, right? So these are our sample space. Okay, this is another example. So it can be viewed as a head and tail, and then we flip the coin 3 times in a row. Okay, and then now the next notion or concept is called this event. So event is basically a subset of the sample space. So our sample space is called, we can view it as a universe because that covers all the possible cases. So we can think of it as universe set, or in Korean it can be called 뭐라고 부를 수가 있죠? 전체 집합. 네, 전체 집합. So this is our universe set, and then this event is basically any type of a subset of this universe set. Okay? Subset means, in Korean, 뭐죠? 네? Subset. 부분집합이죠? 부분집합. 네. So in the probability world, so subset of the sample space has another name of this event. Okay? So one example of an event is like, okay, so we'll roll a dice, and then the event is those events that where you see the dice value of less than 4, okay, and then it will include 1, 2, 3, and then 1, 2, 3 will be still a subset of the entire possible cases 1, 2, 3, 4, 5, 6, right? So that way we view that as a subset, and which we call this event. And then complement. So here basically we are mainly dealing with the set and subset and so on. So that way we can also think about this complement and also intersection and union. Okay, so complement in the word of set. So what is it in Korean? Or so we consider the set A, and then we can consider this as A complementary. 여집합이죠, 여집합. Yep. So in the case of an example that I gave, like the event that you see as a dice value as less than 4, and then the complement event will be more than 4, or more than or greater than or equal to 4. Okay. Okay, so in this case, we denote that as A dash or A prime. And then this intersection is this guy in the world of set. Yeah, this is basically an intersection. And mutually exclusive and disjoint means, so we consider two sets, okay, A and B. And in the world of a probability, that will correspond to event, right? So those two events, if they have no intersection, or intersection of these two sets is just an empty set, like this, and then we call that as mutually exclusive. Okay. So in practice, once you see the event of an A happened, and then you can guarantee that any of the event, any of the sample belonging to B didn't happen at all, right? And then union is this guy. Okay, so in terms of an event, it means the event A happened or B happened, right? So that's the interpretation. Yeah, so there are many different examples. Okay, and then now, so suppose you flip a coin, okay? So that's kind of one part of your sampling process, and the other part is like rolling a dice, and then you consider like a joint space, or so suppose your one element in your event space is coin, comma, and then dice, and then it could be head or tail, and this could be 1, 2, 3, 4, 5, 6, right? So altogether, we know there are 12 different cases, right? So 12 different cases will form our entire event space. So how can we calculate this number 12? It's just simply by multiplying all the different cases from one part and then the second part. There are some available C's in front. Okay. And then the permutation. In Korean, what is it? 순열. 순열과 조합이 있죠. So this is a 순열. Permutation take into account the orders, right? So suppose you have like 10 different balls that have a different number ranging from 1 to 10. Okay, suppose you pick up like 3 balls, and then you consider or you differentiate different orders, even though you obtain the 3 exact same samples. Okay, so out of 10 you sample the 2, 3, 7, but it can have a different orders, 2, 3, 7, 3, 2, 7, and so on, right? So if we differentiate these different orders, and then we call that as a permutation. But if we do not differentiate these order, and then we call that as permutation이 오더를 구별하는 거고, 구별하지 않으면 뭐라고 그러죠? 네? combination, right? Okay, so you know this factorial, right? And then 0 factorial is defined as just 1, even though it doesn't make sense. Then so in the case of 10p3, which is exactly the same example that we saw earlier, then it is computed as like this one. How many? Should it be 7 or 3? 7 or 3? 7, right? Because it's like 10, 9, 8, right? So factorial should always go down all the way to just 1. So 10 factorial means 10 times 9 times 8 and all the way to times 1, right? So we have to cancel out all the 7 factorials so that we can obtain this. Okay, and then when the circle is involved, we have to divide it by n. Okay, so suppose you want to rank like 4 different items, 1, 2, 3, 4, and then all the possible different ways of like placing them in a different orders, or the different ways of ranking them will be, of course, 4 factorial. But your table, suppose your table is just a circle, okay? So there are 4 sets, okay? So in this case, since the circular table can rotate, so 1, 3, 2, 4 is the same as like 4, 1, 3, 2, right? Which is like a little bit rotated version. So they should be considered the same. So for each of these cases, there are 4 redundancies exist here. So overall, after we computed this, we have to divide it by 4 because all the 4 of different cases is considered as just 1 because we just have a circular table. Okay, and then still is a permutation. But now we have 10 items, and then we have 3 bins, and then in each bin, we place or we put 4 items and 3 items, 5 items, and 1 item, and then within 4 items or 5 items or 1 items, we differentiate the order, and then it could be 10 factorial, 4 factorial, 5 factorial, and 1 factorial, and so on. Okay. And then when it comes to the combination, where we do not differentiate the orders, okay. And then we just place like 4, 5, 1 items into 3 different bins or baskets, but within each basket, we do not differentiate the order. And then it should be like in this equation. Yeah, so basically, all of these are already familiar to us. So okay, you guys know like 10 combination 3 is 10 factorial, 3 factorial, and 7 factorial, right? And then this is the same as 10 combination 7, right? So it means selecting 3 items out of 10 without considering the orders. Okay, again, selecting 3 items out of 10 is exactly the same as selecting 7 items out of 10. So in the first case where we selected 3 items, or we picked up 3 items, and it's exactly equivalent to select the 7 items that are not selected or that remains in the back. Okay. So that way these two are the same. Okay, now back to the probability. So there was a sample space, which is our entire set of all the possible events, right? And then basically the event is basically a subset of our universe. And then that event A has the probability, right? And that probability cannot be more than 1 or cannot be less than 0. So all the probability, which is basically a subset of the entire space, which is our sample space. Again, I'm emphasizing, or I keep saying this: a sample space and event, and so on. So those two words are probably a little bit new terms that to you guys. So you can just memorize those two terms. But all the basic concepts, or like how it works, is quite easy and straightforward to you guys, I believe. So yeah, and then we can consider multiple different events, and then they are, if they are mutually exclusive events, and then it means they do not overlap with each other, or their intersection is an empty set, which means they cannot happen at the same time. Okay? It is not possible. In that case, the union of all these events and their probability is just a summation of probability of each event. Yep. Okay, and then in the case of a dice case, our universe or sample space will have the elements of 1, 2, 3, 4, 5, 6. Okay, and then suppose our event A has only those 4 entries: 1, 2, 4, 5. Okay. So here we will introduce, or we think of additional assumption that each of these single event, single event has the equal probability. Okay, so that is another assumption, and in that case, it's just the probability of this event A is simply just the ratio of these counts of the entire sample space and their cardinality, or the number of elements of this should be U, or this should be the sample space, right? And then n of A. Okay, so that way it will be 4 over 6, right? So that's what this equation says. But let's just let me just note that the additional assumption that we had. So each event, a singular event, each individual event should have the equal probability. Okay, but if our coin is a little bit manipulated, okay, by some casino or those like a little bit bad guys, and the probability of seeing 1 out of 1 through 6, and then the probability of seeing 1 is a little bit higher than seeing other numbers, and then this equation will not hold. This will no longer be true. Okay. Okay, so in these cases, we consider 2 situations or 2 events of A and B, but here they are no longer mutually exclusive or disjoint, which means intersection of A and B has a non-empty set, and thus they have some probability. So in that case, it can be computed in this form. Okay. And then in the case of a union, if those two events are mutually exclusive, then it's just a simply addition of these two probabilities. Okay, if we have more than 3, more than 2, and then it's also simply extended in the same way. Okay, and then here we see another term of a partition. And partitioning, or yeah, so is there anyone who heard about the clustering? Clustering or classification or regression? Clustering. No one heard about the clustering? Classification or regression? None of you? Okay. So classification and clustering, classification, regression, and clustering are the 3 main topics in machine learning and artificial intelligence. And clustering is the same as this partitioning, or have you heard about the k-means? K-means? No? K-means algorithm? Okay. You guys are so young. Okay, so let me introduce them next time if we have a chance. So we have a lot of slides left in this chapter. But basically, this back to this partitioning. So partitioning is basically partitioning the entire space U. Okay. So in this case, A, B, and C. So this is a kind of general Venn diagram that we see, right? But in this case, A, B, C is not a partition of U because there are still some spaces or these regions that are not covered by A, B, and C, right? So in this case, we do not call that as a partition or partition, okay? And also, in the case of partition, I mean, if A1 through AN is partition of sample space S, which is our universe or entire set, okay? And then A through N, if we consider their union, and then those unions should cover the entire space U, okay? So there should be no space like this, okay? And also there is another condition so that we can call them as a partition, which is their pairwise intersection should also be 0. So among these different subsets or events, A1 through AN, you pick up any of these 2 subsets, and then there should have no intersection. Okay? So in that case, we call that as partition. So basically, it's like we partition our space like this. Okay, so this is A1, A2, A3, A4, and so on. So that way, they cover the entire universe, and also they don't have any intersections between any of the 2. So in that case, their union and their probability is simply sum up to 1. But if they have some overlaps, just like this, okay, and then we know this type of union and their probability is computed in this manner, right? And then A and AC. So whatever subset A you choose, if you consider a complement, and then automatically, it's always the case that A and AC is partition of the universe or our entire set, right? So that way, if we sum up the probability of these 2, then it will be always 1. Okay, then Now, just a little bit interesting notion of conditional probability. So conditional probability of event B when assuming the event A happened, okay? And then we can consider that probability. And then this guy is defined as like this, right? I'm just rewriting this equation. And then, let's see. Our universe and this is like 0.7, and this universe, the area is 1, and this one has the area of 0.7, and this is called A, and then B is something like this, okay? And then this part is like 0.5, and this intersection is like 0.2. So let's think about this situation. And then what is the probability of B given A? So first of all, what is the probability of A? A was 0.7, which was the area of this part, 0.7, and P of B is 0.5, and then the intersection A and B is 0.2, right? And then this cannot be bigger than those two, okay? And then this probability is, can anyone tell the answer? 네, 얼마죠? 네, 7분의 2. Yeah, that is right. So in this case, so we consider we consider A already happened, right? So we do not consider any of the cases outside of A. So 0.7 becomes our universe. So out of this universe of 0.7, the probability of B happening is only 0.2. So the ratio between 0.7 and 0.2 will be our conditional probability. And then it can be represented as this guy, right? The event or the probability of A and B simultaneously happening, and divided by the probability of A. Okay, so that is the definition of this conditional probability. Okay, let's skip the example. And then now here's the notion of the independent or independence. So if the two events are independent, then we consider the condition, the independence is true when these two equations are hold, and automatically if one is true, and then automatically the other is also true. Okay, so that is a little bit interesting relationship between those two. And then so their like intuitive or their interpretation is that the probability of P of B, regardless of A, whether A happened or not, so probability of B is the same as the probability of conditional probability of B happening given A happened, A happening. Okay, then so let me give one example just to help you like understanding about what this really means. So overall, suppose so we think about the height of a person, whether it's a man or women. I'm sorry, this is a really boring example. but not the creative. But anyways, so if we consider those height as our samples, and then the sample space is all the possible heights, okay? All the possible heights. But we have to remove the redundancies. So if one student is 170 centimeter and I'm also exactly 170 centimeter tall, and then only one instance of them is included in our set because of the definition of the set. Okay, so all the possible values of this height will be our sample space, and then let's consider the probability of the height being higher than 180. Okay, and then the probability of height being more than 180. Okay, like this. Suppose that probability is like 20% or 0.2. Okay, and then so it's this probability is regardless of whether that person is man or woman, right? So altogether, yeah, regardless of men or women, overall the probability of height being more than 180 is 0.2. Okay, but suppose we obtained additional clue or additional like information that the sampled person is actually a man, okay, and then that can be represented as man. Okay, in this case, suppose that probability. So would this probability be more than 0.2 or less than 0.2? More than 0.2, right? So let's say it's 0.3, okay? In this case, this additional information of knowing that this sample is actually man changes the probability of height being more than 180, okay? So this additional information is definitely influenced the probability of this event, right? So in this case, the height and also this gender is dependent, right? But if this probability still remains the same, and then these two events are called independent. Okay. But in this case, it doesn't. We do not feel it makes sense, right? But let's consider another type of an event where this is changed as region, okay, and where they live, and then so this guy is changed as maybe Seoul. So now instead of additional information about the gender, suppose we additionally obtain the additional information that this guy is living in Seoul instead of Busan or Gyeonggi or any other area. Okay, so in that case, that additional information is not expected to change this probability of the height being more than 180, right? So in that case, yeah, we can think that this region and the height is not related. They do not influence each other, right? So that's the example of this independence. Okay. Okay. And then we consider this intersection of the case where A and B happened simultaneously, and in this case it can be written as this guy. So in this way of equation, in this type of an equation, we kind of consider the sequence or the orders of these two events, A and B. So in this case, so we can consider the event A happened first. Okay, at this moment, we don't know whether B or B happened or not. Okay, so first A happened, and then given that situation, where we know that event A happened, And then we consider the conditional probability of B happening, okay, given this situation where A happened, okay. So that is corresponding to this probability of P of B given A. So if just multiply these two together, these two terms together, and then we obtain the probability of A and B simultaneously happening. Okay. Okay, I just skip this example. Okay, and then now we consider the event where A and B simultaneously happening, right? So in this situation, we know this is true. A and B can be viewed as A first happened, and then given A happened, we multiply the probability of event B, right? But in this case, the definition of independence was this guy, right? So this one was the event of height being more than 180, and that is not related to like a region, right? So we don't, even if we do not know the information about the region, the probability of height will still remain the same, right? So in this case, we know this one is true in the case of independence, and then we just plug this guy here, and then we obtain this. Okay. Oops. Yep. So that way, when the two events simultaneously happen, and then we can, if they are independent, and then we can just simply multiply the probability of separate events. Yeah, I just skipped also this example too. Okay, and then we consider these more than two events simultaneously happening. Okay, so suppose we have three events: A1, A2, A3. And in this case, if we consider the order of these events, and then we can write this guy. So first of all, A happened, okay, without knowing B or C happened or not. And then given A, B happened. Sorry, this should be A1, and A2, right? And then the third situation is that A1 and A2 happened, and then A3 finally happened, right? And then if those events are independent of each other, and then this one will become P of A2, and this one will become P of A3, right? So it's extended from the two case to more than two cases in this simple way. Okay. Okay, now we are at the 52, second slide, which is about this Bayes rule. Bayes rule. Okay, so Bayes rule is this guy. P of B given A is the same as P of B. A given B times P of B divided by P of what? A or B? Yeah, this should be A, right? right? Yeah, it's true, right? So yeah, this is basically a Bayes rule, and then from a slightly different angle. So let's consider this. Okay, so the situation where A and B simultaneously happen. Okay, so in this case, in general, we can consider their orders. Okay, so there exists two different orders. So the first order, the first order will be A happening first, and then B happened when A already happened, right? And then also we can switch the orders with no problem, right? So let's consider B first happened, and then A happened next when B happened already, right? So these equations are true, yeah, regardless of like independence or not, right? So it's always true. And then in this case, if we focus on these two, and then we bring this guy here, and then it's simply this guy divided by this, which is this part, right? So that's how we can kind of understand this Bayes rule in a, I guess, the most simplest way. Yep. So yeah. So basically, this Bayes rule allows you to change the sequence or the orders of these multiple events. Okay. And then let's see. This is not exactly a Bayes rule, but this is the most important point. But let's follow this theorem, which is slightly different from the Bayes rule. So here the situation is B1 through BK are partitioning, or it's a partition of the our entire space S. Okay, and then we consider another separate event of an A, and this event, the probability of event A is, let's see, so yeah, so this figure is illustrating the situation very well. So this is our universe, and then B's are partitioning our space. So this part is B1, B2, B3, and so on. So they are mutually exclusive, which means they have no intersections, or intersection is always empty set, and then altogether the union is cover the entire space S, right? And then we consider this another separate event A, okay? And then probability of A, or the area of this part is composed of this part and this part and this part and this part and this part, okay? So this part is corresponding to the case of A and P3 happened simultaneously, and this part is A and B5, okay? And also B's are mutually exclusive. So every pair of B's do not have any intersection. So we can just simply sum up together all these areas, and then there is no redundancies. And so after summing up these areas, and then we will always have the same area of the original A, right? So that's this equation. And then also this guy, this intersection probability is represented in this form, PB3, and then A happened after B3, right? So we can change this guy into this form. Okay, so I guess time's up, and so we will continue next time from this point. Okay. Okay, thank you very much.